Okay, so this is Blue Volume 3 review session, and I will also go over Volume 4 after this. Okay, so here's just a quick table of contents for our Calculus Blue Volume 3. What all we did was everything that we did included like double integrals, triple integrals, all those different like applications, and of course substitutions and surface integrals. Okay, so first topic, double integrals. So double integrals, we have the idea that you're always going to have some 2D region. And we have important theorems. So Fubini's theorem of the first form, that's only for rectangular regions. So what this theorem says is that all of your bounds are going to be numbers. And so if you want to switch the ordering of your integration, so like if you wanted to do dx dy or dy dx, you don't have to think. You don't have to think about anything. You just have to switch the bounds and switch the lettering. But then we have the stronger form of Fubini's theorem, which we typically is the one that we use, and that tells you like how you're supposed to find your bounds. So the idea you always want to use here is that your innermost bound can be expressions with whatever variables are left. So like if we're only considering this first integral, these bounds can have x's in them or constants, but your outermost bounds can't have any variables at all. They have to be only constants because there's no other like number variables left over here. Okay, and some properties of double integrals are you have the constant multiple rule. So like if you're multiplying by a constant, you can take that constant out. Sum and differences, just like normal integration, you can separate addition and subtraction by doing double integral of the first thing, and then plus or minus the double integral of the second thing. And we also have additivity. So this is where if you're trying to find the area, for example, of this entire square region, we could split it up into two integrals and say we have the integral over this first region, R1, and then we add it with the integral over the second region, R2. So that's like additivity. You can also find area using double integration. So remember that we always have, if you're trying to find a smiley face, it's integral of d smiley face. So if we're trying to find area, we can do double integral of dA. And whenever you see double integral of dA, there's always like an implicit one there. So you can think about why that means area. And we also have average value. So that's where whenever you're finding average of something, it's always you have some integral on the top and you divide by that same integral, but where you have one in the integrand. So if you're finding like average area, we have double integral of your function over double integral of 1 dA. But double integral of 1 dA is exactly your area. Okay, any questions so far on these double integral rules? Okay, then we can move on to triple integrals. So a quick refresher of triple integrals. We also have Fubini's theorem for triple integrals. So here we see that like you want to make sure that your bounds are always correct, meaning we look at the first inner thing. So let me highlight this thing. And whatever bounds you have here, they can have y's, x's, or constants in them. Then once we do that integration, you've eliminated a variable, you've eliminated z. So now when we look at this next integral, the bounds here can only have x's in them or constants. They can't have any z's because we've already eliminated those z's. And then as always, the outermost bounds should always only be numbers, constants. Okay, and how do we find the bounds for triple integration? Well, we follow a process. Usually we start with z first. So like for z, we have some 3D shape. For example, say we have a sphere. And you imagine cutting a line through your object in the direction of increasing z. So I like draw a line in the increasing z direction. And I see what surface does it enter through first. It enters through this bottom like hemisphere surface. and then it exits through the top hemisphere surface. So those would be our bounds for Z. Then we always collapse whatever like axis that I choose. So since I did Z first, I will collapse the Z axis. And what I'm left with is a circle in the XY plane. And so now I can do my normal double integration rules, where I can draw a line in the increasing Y direction, for example. Then I could do dy dx. Or if I wanted to do dx dy, I would draw a line in the increasing X direction first. Whatever curve it enters, that's my lower bound. Whatever curve it exits, that's my upper bound. Then out of all those possible lines I draw in the increasing X direction, smallest Y value would be my lower bound. Largest Y value would be my upper bound. And just like for double integrals, for triple integrals, we have that the triple integral of 1 dv tells you the volume. And we also have average for triple integral. That would be triple integral of some function over triple integral with 1 here. But triple integral of 1 is exactly what volume means. Okay, and so we also have properties of triple integrals. We still have linearity, just like we had in double integrals. If you're multiplying by some constant, you can bring that constant out. If you're adding, you can separate the addition. And we also have additivity as well for triple integrals. Okay. So for example, we can do, so this is just a bunch of integration techniques. So I've written out all the work here, and you guys can check. But say we're considering this integral, I can do all of the work and I get 1. Then a question that they could ask is, does your answer make sense? Like, is your answer positive, negative, or 0? And does it make sense? Well, for this question, we did all of the integration, blah, 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 and we got 1, which is a positive number. So our answer is positive. But why does a positive answer make sense? Let's look back at our integral. The first reason a positive answer for this integral makes sense is you want to say that the integrand is never negative. So you always want to see, first thing is look at the integrand. We know that the integrand is never negative because look at our z bounds. Z is from y squared to square root y. Doesn't seem like there's anything wrong there yet. X, it has -4. So you might say, oh, the x is negative. But look at our integrand. Our integrand doesn't have any x's in it. So it's fine that the x bounds go from -4 to 2. Because our integrand is only considering y and z, and we see all the y and z bounds should always be in the positive like quadrant. So our integrand is never negative. And 2, our bounds are well ordered. In other words, our bound should always go from some smaller number to a larger number. And we see we have x goes from -4 to 2. That's correct. That's the correct order. And y is 0 to 1. That's good. What about z? Let's imagine what the z bounds look like. So if this is y and this is z, z goes from y squared to square root y. And so we do go from some lower bound, some lower curve to a higher curve. So z is also well ordered. So the fact that this answer that we got, which is 1, is positive makes sense because of these two things. Integrand is never negative and bounds are well ordered. Okay. Any questions on that?
When would the integrand be 0? Or yeah, when would it be 0?
It would be, so the integrand can be 0, like specifically when y is 0 or z is 0, at that like specific point, your integrand would be 0. But because we have other points as well, then that's what makes this integrand like a positive number, because you would have 0 plus something else plus something else. Your integrand, I guess, if your answer was 0, like what does that mean? That would mean that either you have, for example, some sphere and the integrand in the top is some positive number, and the integrand in the bottom is the same number but negative, then you see that the numbers would cancel out and you get 0. Or in general, if you have triple integral of dv and you get 0, well, triple integral of dv, that's volume. And if volume is 0, that means that you have no like 3D shape. Your shape is flat. Okay. Other questions on that? Okay, so we can also consider this. Let's try this question. So we have a double integral here, and it's important that we all remember how to reverse order of integration, like drawing things and then reversing the order. So let's try this. We have a double integral. We start with y. So let's draw what y looks like. The y bounds. Okay. So y goes from x to the fifth. Now I don't exactly know what x to the fifth, like I might not know what x to the fifth looks like, but I do know what y equals x cubed looks like, right? Because x cubed, this is an odd function. So no matter what, my graph would have one direction going up, one direction going down. So I know that y to the fifth, it's also an odd version, odd power. So it should have a similar behavior. One side should go up, one side should go down. So y to the fifth or x to the fifth looks something like this. I don't know exactly what it looks like, but it should have this behavior. And then what is the upper bound for y? It goes to y equals cubed root of I. Now, sorry, I might not know what cubed root of y looks like, but I should know what square root of x looks like, right? Square root of x looks like this curve. And so that I know cube root of x should also look something like this, just the numbers might be smaller because it's a cubed root instead of a square root. And so y x cubed, sorry, 1/3, yeah, cubed should look something like that. And so the region that I'm considering is y, drawing a line in the increasing y direction, enters the blue curve, exits the orange curve, that's good. Smallest x value is 0. Largest x value is 1. 1. So this is the region I'm considering. Now to reverse the order of integration, what do? Say I want to do dx dy now. That means I draw a line in the increasing x direction. What curve does it enter first? It enters my orange curve. But I need to write it as x equals something. So if my orange curve is y equals x to the 1/3, that means if I cubed each side, I get y cubed equals x. So I get x equals y cubed is my lower bound. What curve do I exit? I exit the blue curve. And that blue curve, if I rewrite it as x equal to something, that's x equals to y to the 1/5, because I take the power of 1/5 to both sides. And then out of all those increasing lines I can draw in the x direction, my smallest y value is 0 still. Largest y value is whatever this point is. What is that point? Well, it has a x value of 1, which means when I plug it in, y should also equal 1. So that means my upper bound is y equals 1. And then I keep my integrand the same, this 3 plus 2xy. So that's how I reverse my order of integration. Now, without computing this integral, can I kind of guess what it's going to be? Is it going to be positive, negative, or 0? Or can I not tell? So here, what are the two things we have to consider? In the last example, we considered what's the integrand doing? And what are the bounds doing? So let's first look at our integrand, 3 plus 2xy. Well, I graphed my region here, right? This is my region, which means that no matter what x and y values I plug in, the x and y values come from my region. And so all of those values are going to be positive, which means that when I plug those positive numbers in here, this 2xy is also going to be positive. And so my integrand is positive, no matter what, according to my region. Next, I look at my bounds. Are my bounds well ordered? Well, they are, because x goes from 0 to 1. 0 is a smaller number. And y starts at x to the fifth. And x to the fifth is the smaller like curve. And so our bounds are well ordered. So I would expect my integral to be positive because of these two reasons. Any questions on that? Okay, and so I have a little summary here, which is all the double and triple integrals that we've done so far. So we have, if we're trying to find the area of a region using a double integral, notice that it has double integral 1 in here. If you do a double integral with a function in here, that tells you the volume. If you do a triple integral with 1, that tells you the volume as well. And triple integral with some function is going to be some 4D thing that we don't really know of. And then we have our average formulas, of course. This is kind of like a little summary. Okay, let's move on to any questions so far?
I got a little confused when you're just saying how you could tell the value, the positive, negative.
Yeah. So the two things we want to consider when looking at the value of an integral is we want to look at the integrand and we want to look at the bounds.
Mhm.
So first looking at the integrand, well, I'm integrating 3 plus 2xy over this region. So all of my xy points, x comma y points, are going to be coming from this highlighted region, which means that all the x and y's have to be positive. And so what is integration doing? It's like I'm plugging all those values into this integrand, 3 plus 2xy. Since x and y are both positive, that makes 2xy also positive still. And 3 plus 2xy, well, you're adding 3, so it's still positive. So my integrand, this 3 plus 2xy in this region, like evaluated with points from this region, is always positive.
Okay.
Yep. And then our bounds are well ordered because bounds being well ordered means the lower number should be smaller, upper number should be bigger. And 0 is less than 1. X to the fifth is also less than this in the sense that when you draw a line in the increasing y direction, our x to the fifth line does come first.
Okay. Thank you.
Any other questions on so far?
I have a quick question on the summary.
Mm-hmm.
So the second column, first row, states that a double integral can represent a volume. Is that not that one, the one next to it? Yeah, that one. Is that like the volume under the surface?
Yes, like the volume under, yeah, this function kind of.
Okay, but it could also represent like you're integrating a density function over 2D, right?
Yes, except we don't have a dense, like there would be a row here. So like unit density.
Oh, okay, thank you.
Yep. Okay, and that's a good segue to our applications. So where we'll talk about density and stuff. Okay, first application is applications in geometry. So here I've written again the different cases. So we have n equals 2 case, meaning if we're in 2D, you have all of these formulas. So we're thinking about applications in geometry. When we think of geometry, those are like shapes. And so the natural thing to think about is like, what is the area of a shape? What is the volume of a shape? So for n equals 2 case, these applications in geometry, we always have an area element. So that's always the variable. dA is dx dy. And then area is always integral of the area element. So that brings us to the smiley face equals the smiley face idea again. To find anything, we always integrate this element of that thing. So area is integral of the area element. And then we have the average value function, which we saw before. And now the new thing is the centroid. The centroid is a bit different from the average value in that when we're doing the centroid, it has two components, the x component of the centroid and the y component of the centroid. And how you find those is you're still dividing by your area, except on the top, you want to put an x in the integrand. And for the y centroid, you put a y in the integrand. And then for the 3D case, we have volume element. So if we integrate that volume element, we get volume. We have the average value for triple integrals. And we also have the centroid for 3D version. So it's the same formula, just you have an extra like z bar.
Quick question.
Mhm.
So when you find those integrals, that would be like your coordinates, right?
Yes, those are like your coordinates.
Okay.
Yep, so to find the centroid of some region, if you're in 3 dimensions, you have to find each of these things and then you write your answer together. This is like, because if you think about if you have a sphere, what is like the center of that sphere, assuming we have unit density, the center is like the origin. So when you compute these integrals, you would get like 0, 0, 0. So you would say the centroid is that x bar, y bar, z bar. Okay. And so we can do an example. If we want to consider the following region cut out by the graphs of y equals square root x and y equals x squared, and we want to find the y coordinate of the centroid. No matter what, when you see these questions, always just draw the picture, because you can always get, like, you can see if you understand the question by seeing if you drew the right picture. So cut out by y equals square root x. So let me draw square root x. I should know that looks like this. Y equals x squared. I should know it looks like this. And so my region is the shaded in region. So I can, assuming I'm on paper and pencil, I could just do like that. Okay, so what is y bar going to be? It's going to be y dA over 1 dA. The only thing I have to consider is what are my bounds going to be. So for this question, it doesn't matter which order you choose. Let's just do dy dx. You could also do dx dy if you want to. So how do I do dy dx? I draw a line in the increasing y direction. What curve does it enter first? It enters my x squared curve. Y equals x squared. What curve does it exit? It exits the square root x curve. Then out of all possible vertical lines I can draw, what is the smallest x value? That's 1. What's the largest x value? Well, whatever point this is. How do I find that point? I can do a little bit of algebra, meaning I set x squared equals to square root x, which means x to the 4th equals x. In other words, x cubed equals 1. So I divided by x on both sides. And so I get x is plus minus 1. But I know it's going to be positive because I'm in the positive quadrant. That means x equals to 1 here. Sorry. And my lower bound, I wrote it wrong. It was 0. So you can either, to find this point, set these equations equal to each other, or I can also kind of guess, because like 1 squared equals 1, square root of 1 equals 1 as well. Okay, and the bounds for the lower thing are exactly the same. I keep everything the same. And you can evaluate that by doing some integration. I'll tell you guys the final answer is 9/20. Now we can ask, does this answer make sense? Again. So we got that our y coordinate of the centroid equals some positive number, 9/20. If we think about the centroid, what is it doing? It's kind of like find the average y coordinate, like the middle coordinate. And looking at our region, what is the middle like number of y? The middle is probably like somewhere here, something like that. So in other words, all we know is the average y coordinate should be positive based on our region, because it's like in the middle. And so since we did get a positive number, our answer does make sense. Because first of all, it's positive, and also because we see that the domain of our, or like the bounds of y are 0 to 1. Those are all the possible y values I could get. So it makes sense that the average of y should be between 0 and 1. Okay, any questions on that? Okay, so next we have applications in mechanics. So now we deal with density stuff. So for mechanics, we again have the 2D case and the 3D case. We have a mass element. If we integrate the mass element, we get mass. Now, instead of centroid, we have kind of the analog in mechanics, which is the center of mass. And the center of mass is similar to the centroid equation, except the only difference now is we have these densities added in here, the rows. And with this, we also have a formula for moment of inertia. Moment of inertia is r squared dm. But don't forget this dm, what I always mean by dm is that it should have a rho dx dy. So don't forget that density. You always need a density. And then you have radius of gyration, which is square root of I over m. You also have the 3D version for this. So everything's the same. We just add a dimension. And for the center of mass, you add a z bar. Okay. And during this week, we also did the parallel axis theorem. So the parallel axis theorem is where, for example, they give you that the moment of inertia through this circle with radius, with like axis as the y-axis. They give you that the moment of inertia is some I naught. But say you want to find the moment of inertia through the x equals 2 axis. So I want to find what is the moment of inertia through this axis. Well, this purple axis, it's parallel to my original x equals 0 axis, the y-axis. And so I can use the parallel axis theorem to say that the new moment of inertia is going to be the old moment of inertia plus either you find the mass or they've given you the mass plus m. And d is the distance between your two axes. So because I moved over to the x equals 2, I should multiply by 2 squared because it's a distance of 2.
So nervous. I'm not like, it's fine. I don't have my hopes up or anything. They said they were going to call tomorrow.
Okay. So we also have another concept. So how does like mass and centroid, center of mass and the centroid relate? Well, it turns out that if your density is constant, then the center of mass is going to be exactly the same as the centroid. So recall that for the center of mass, the formula, for example, of the x coordinate was we had x rho dv over rho 1 rho dv. And the centroid was the same formula, but without the rho. So if you imagine that your density is constant, meaning this rho is 1, then you see how this formula will give you the same thing as this formula. And so if we're trying to find the center of mass, that's like a feature of geometry. So we don't really have to do any calculations necessarily unless they are definitely needed. If they're in general, we can instead kind of look at the shape. So for example, we have this paraboloid. And we want to find the center of mass, assuming density is constant. So here, this is a 3D shape. So we should have 3 coordinates for our center of mass or our centroid. What is like the x, the center of x, the average value of x? Well, we see that x is kind of symmetric. We have values all positive, values all negative. And so the middle of that is 0. The x centroid should be 0, assuming density is constant. The y centroid should also be 0 because our y is symmetric. We have positive y values here, negative y values here. So if they say what is like the hard coordinate to calculate, you would say the z coordinate is the hard one to calculate. Because here we can't just say it's 0. Like it might be the center of mass is like this purple point, but what is that purple point? I don't know what it is. So I have to actually calculate it and say it's going to be like triple integral of or double integral of z dx dy over, actually, let me make it triple integral 1 dz dx dy. Okay, and so we have another example here, the cylinder thing. We can kind of guess again. 2 of the coordinates should be easy to calculate. 1 of the coordinates should be hard. So you want to look at like, what is the middle x value? Well, it looks like x is symmetric. So the middle x value is, or the average x value is 0. The z also looks symmetric, right? We have like half of our cylinder in the top, half of our cylinder in the bottom. So z should also be 0. And y bar is the hard one to calculate, because I don't know where the middle of y is. Like the middle of y could be here, that purple point, but I would have to actually find what that is. Okay, any questions so far? Okay, and so we can do a practice problem. So let's consider a rectangular prism defined by these bounds. So meaning we have some rectangular prism, x length is L, y length is 2L, and height is 3L. So I've drawn our picture here. This body is assumed to have unit density. And question 1 is, what is the moment of inertia rotated about the y-axis? So first, as a side note, I said, let's first find the mass actually first. So what is the mass? Well, mass, I've written out the formula, is triple integral dm. In other words, triple integral rho dv. So mass equals triple integral of our rho. We said it's unit density, which means rho is 1. So we have mass is 1 dv. What is triple integral of 1 dv? That's exactly volume, right? Because remember, smiley face equals integral d smiley face. So we have volume is triple integral dv. Okay, and what is the volume of my prism? Well, this is a rectangular prism, so it's length times width times height is volume. So length times width times height, as given in the problem. So it's 6L cubed. So we have that the mass is this. Now we can find the moment of inertia. What is moment of inertia? That formula is I equals triple integral of r squared dv. And I didn't write the rho there because we have unit density, so a 1 is assumed. Okay, what is r squared? How do I find r? R is the distance from any arbitrary point to the axis that I'm rotating about. I'm rotating about the y-axis. So if I pick a point, an arbitrary point, let's call it xyz, and I want to find its distance to the y-axis, meaning like the closest distance it has to the y-axis. Well, that closest distance is, it's going to have the same y value, right? But x and z will be 0. That's the closest point that xyz has to the y-axis. And so now I use distance formula. Distance formula says the distance between any 2 points is square root of, we have z minus 0 squared plus y minus y squared plus x minus 0 squared. So we have z squared, y minus y 0, and x minus 0 is x squared. So we have triple integral of r, which is square root z squared plus x squared dv. In other words, we have, let me make some space, z squared plus x squared dv, because the square root and the squareds canceled. Now, what are our bounds? Well, whenever you see some rectangular shape, like if it's a square, if it's a cube, if it's a rectangular prism, that's the nicest shape they could give us, because our bounds, we just have to look at what their like length, width, and height are. Because the bounds for any cube, square thing will always have constants. That was Fubini's theorem, like rectangular version. And so if I wanted to do d, let's say dy, dx, dz, for example, then it doesn't really matter what order I do them in. I can write the bounds as what their lengths are. Y went from 0 to 2L, X went from 0 to L, and Z went from 0 to 3L. Okay, and I can do, this is very long integration, so I will let you guys look at it in my notes. Okay, then we have an additional question, which is, we got our answer. What happens if I want to rewrite it in the form I equals CML squared? What is I? I is 20L to the 5th. And I want to write it as some constant C, this is a constant, times the mass. What is my mass? I found it up here. It was 6L cubed times L squared. So I want to find what C is. Well, now I have an equation, and so I can solve. This is 20L to the 5th equals to 6C L to the 5th. L to the 5ths cancel. So I have 20 equals 6C. Solve for C. C is 20 over 6. Or simplified, 10 over 3. So I found the constant. Okay. And part C says, actually, I don't know if these are parts. Maybe I made this up. Yeah, maybe I made these questions up. So set up the integral to compute C bar. Well, what is C bar? We recall the formula, triple integral of y dm over m. Well, we have unit density right now, right? So these things are V1. And so our y bar is going to be triple integral of y dv over triple integral of 1 dv. These bounds are going to be the same exact bounds we used above in the purple. Y equals 0 to 2L, X equals 0 to L, D equals 0 to 3L. We use the same bounds because it's the same region still. It's that rectangular prism. ln y, dy, dx, dz. What about triple integral of 1 dv? This looks familiar. This looks familiar, or it should look familiar, because that's how we found the mass above. We had triple integral of 1 dv, which was 6L cubed.
I have a quick question. What is, like, when we did the centroid earlier, it was just y dv over v. So why is it dm though?
Yeah, so it turns out that because we have a unit density in this question, calculating the mass is the same as calculating the volume. And that's because we look at our formulas, right? So mass is triple integral of rho dv. But because we have a unit density, rho is going to be 1 dv, and triple integral of 1 dv is volume. So when we have unit density, mass is the same as volume. And
Okay,
so that's,
thank you.
Yep.
But usually when we're calculating the centroid, we're going to be using the volume, right? Like dv over v?
dv over v. Only if you have unit density. If your density is something else, then it won't be just volume on the bottom.
Oh, then it would be mass. Okay.
Yeah, like then you would have to actually calculate it. Like if you had some, like if they gave you like, I don't know, the density is like 7xy or something, then to find the centroid, you would have triple integral of let me write it in normal, triple integral of y times rho dv over triple integral of 1 rho dv.
Okay, got it. Thank you.
Okay, any other questions on that?
Sorry, could I just check? When we're talking about y bar, are we talking about the y coordinate of the center of mass or the y coordinate like for the centroid? Because I thought, like, I think that's kind of the confusion here.
I see. Yes. So we are talking about the y coordinate of the center of mass.
Okay, got it. Thank you.
I'll clarify here. Center of mass.
Can I ask a follow-up question?
Mhm.
So when there is unit density, the center of mass, the coordinates of the center of mass is a centroid, right?
Yes.
Uh.
Yeah. So this question, we're finding the y coordinate of the center of mass, which is why I wrote this formula in blue here. But because it turns out in this specific question, density is unit, that means that our formula becomes triple integral of y times 1, right, dv. And now this formula kind of looks like the formula for centroid, or is this formula for centroid. So in other words, if density equals 1, then center of mass equals centroid. Okay. Now let's do applications in probability. Okay, so probability is slightly different from the applications in mechanics that we just did. So here we have probability element. As always, we always need a something element. And if I integrate that element, I get probability. One thing to note here is that this row here, this is the probability density. This is different from the density that we just worked with above. Like in mechanics or for like the other applications, mechanics, the density could be anything we want it to be. Can be anything. That was just regular density. But if you're dealing with a probability density, what's special about this density is that the integral of it should always be 1. It has to be 1 because when we think about probability, like what's the largest probability you can have? It's always like 100%. So your integral over probability, like what's the like total thing you could get should be 100% or 1. And so sometimes you'll have questions like, what constant makes this probability, what constant, so like what C makes, I don't know, some random like 3x, 3cxy, a PDF, a probability density function. And in order to solve that, that's telling you you want to integrate it and set it equal to 1 and solve for C. So that's a common question for like, if they say like, what makes it a probability density function? Okay, and in the other cases, we saw that there was always the n equals 2 case and n equals 3 case, meaning we always have the 2D case and the 3D case. For probability, we're only going to have generally the 2D case. And that's because like we always think of probability as x and y's. We haven't really thought of it in like 3 dimensions or higher dimensions. Okay, so with the
Excuse me, about the example with the C3xy, doing it after 3xy goes dp or dx dy?
oh, it should be the dA,
Not dp,
not dP, because this is already saying
part of the r.
yeah,
Okay.
this is dP. It's rho
Okay.
d.
Thank you.
Okay, so with probability, we also have formulas for expectation, right? Expectation is going to be the double integral of, now we have these x in here because it's the x coordinate of the expectation. You should have an x there, and then the probability density function, dx dy. For the y coordinate of the expectation, we have a y here. And now for this notation, you see that I've written negative infinity to infinity on both bounds. It's not always the case that it's negative infinity to positive infinity. I wrote this notation to imply that it means your entire domain. Your entire domain. So whatever like region they tell you it is, like you have, you should make your bounds be over your entire region. So like, as a side note, if they said your domain is like x and y greater than or equal to 0, that means that when you're finding the expectation, your bounds will be x goes from 0 to infinity, y goes from 0 to infinity. Oh, because you want your entire region. Okay, and that's for the x coordinate of expectation. So to get the actual expectation, like your answer, you would write it as like whatever you got for the x coordinate and then whatever you got for the y coordinate. And then you have the variance formula and then standard deviation, I wrote standard deviation is the square root of variance. Okay, so let's do an example because this is a lot of formulas. Okay, this is from spring 2017 number 12. Okay, so consider the following probability density function on the unit ball. And part A, this is exactly what I was talking about. What value of K, or I called it C above, makes this a probability density function on this unit ball domain. So how do we do this question? The idea is that I want to set the triple integral of rho dv equals to 1. So that's triple integral of k times x squared plus y squared plus z squared to the 3/2 dv. But I see that this is kind of hard to do, right? Like, what are my z bounds going to be with this sphere? It's going to be like square root of 1 minus x squared minus y squared. Like, to integrate that and then plug those bounds in, that would be a lot of work. So whenever I see this kind of sphere thing, maybe converting to cylindrical will be easier for me to do.
Wait, quick question.
Mhm.
So, like, the actual test itself, is this format like having a box where we're supposed to put our final answer? Is that the way it's going to look?
I believe so. Yes. Let me see last year's. Let's see. No, actually, no. It's gonna be more like the Friday quizzes format.
Okay.
Yep. Okay, so yeah, this was from like 2017, so it was a while ago. All right, so we can convert to spherical coordinates. How do I convert to spherical? Well, spherical coordinates, x squared plus, we had the formula where x squared plus y squared plus z squared always equals rho squared. And so when I convert to spherical, I will have k rho squared all to the 3/2 dv. And when I convert to spherical, what happens with this dv? It becomes rho squared sine b. Okay, and for my bounds, what do I have? Let's look. I have my unit ball less than or equal to 1, so it's my entire sphere. So what should rho be? Rho you want to think of as like what's your starting radius and ending radius. Rho usually starts from 0. What's the radius of your sphere? It's 1. So I go to 1. Phi bounds, I have my entire sphere, no limitations. So the greatest phi bounds I can have are 0 to pi. Because what is phi? Phi is like, what is the angle that you can make with the positive y-axis or z-axis? And that's the entire sphere, so entire 0 to pi. And then theta, we have no bounds, so 0 to 2 pi. Okay, and I won't do this work because we're running short on time, but we get 2/3 pi k equals 1. And so I solve for k. K is 3/2 pi. Part B, set up but do not solve an integral for the probability that a randomly chosen point in this domain has z greater than 0. So what is the probability that z is greater than 0? Okay. And so this question, so that was part A, part B. Let me side note z greater than 0. So this question, we have the same exact thing. So we want a triple probability of z greater than equals 0 equals, it's going to be a triple integral of rho dv. What is rho? I found that k is this, so I can plug in my rho is 3 over 2 pi x squared plus y squared plus z squared all to the 3 halves. Because my rho is this thing and I know what k is. And then I have dv. Okay, what are my bounds going to be? Well, my rho bounds are still, we have a radius, a sphere of radius 1. So rho still goes from 0 to 1. But now for our phi bounds, this is where it changes. Because we have a sphere. But we only want z greater than 0. So we only want the hemisphere. That means that phi starts from 0. But what's the maximum angle it can make with this positive z-axis so that I'm still in my region? Well, I can only go up to here. And that's an angle of pi over 2. If we had our entire sphere, that's why it goes all the way to pi, exactly 180 degrees. Our theta, we don't have any limit, so 0 to 2 pi. And also the fact that I already converted it to spherical coordinates, I should have made my dv rho squared.
Excuse me, shouldn't theta be 0 to pi? Why does it stay the same?
Because we have our sphere and z is greater than 0. So it's just the top hemisphere part. But if you imagine collapsing the z-axis, you still have an entire circle in the xy plane.
Okay, thank you.
Yeah. So you want to like think about a globe, and you just have the top part, but it's still like the entire top part. And so when we like collapse it, we look at the shadow, it's still the entire circle in the xy plane. And so theta is 0 to 2 pi still. Okay.
I have a quick question. So when you're integrating the part A, instead of like doing the whole integration, could you just replace dv with like the volume of the sphere, because we know it's the unit sphere?
So you can't do that because you can only like say that it's the volume of your sphere if your integrand is 1. If your integrand is not 1, then you can't do that. You have to do some either conversion or actually do it out.
Okay.
Okay, part C. Use your without computing the integral, what is the probability? Okay. And also the fact that I've written all these in spherical, let me just write it more correctly. This is rho squared, right? Okay. So without actually computing it, can we guess what this integral might be? Well, what is it trying to find? It's trying to find the probability that z is greater than or equal to 0, which means finding the probability that we're going to be in the top half of my sphere. And we can look at what our integrand is. What is our integrand? It's just telling me, I just have my density in here. And so at points in the top, for example, at this random point, x, y, z, it has some density, has some density. Cool. Let me call it, I don't know, z. No, let me call it b. Okay. And at this point in the bottom, some x, y, z, maybe it's negative z now, it still has density b. Right, because we are in our density function, we always have something squared. So even if your number is negative, a negative number squared is positive. And so you can think about this sphere as being very symmetrical. So no matter what the density is up here, it's going to be the density down here. And so if we kind of found the entire looking at our entire sphere, what is the total probability we can have? Total probability over entire sphere. Well, what is that? That's like integrating rho. And we know because this is a probability density function, integral of rho should be 1. Now, if I'm only doing half of my region, z greater than 0, this is just a hemisphere part. Well, it's only like half of my region. So my probability should probably be a half because everything is symmetrical and we're taking exactly half of our region. So part C is a half. Okay. Any questions on that?
I have a quick question.
Mhm.
So for if rho was not symmetrical,
Mhm.
then would this not be true?
Yeah, then it wouldn't be true.
Okay. And
Yeah,
we saw that rho was symmetrical because of the function, right?
Yes, because of how it's defined.
Okay.
Mhm. Yeah, if rho is not symmetrical, then like you can imagine like what if this part has very high density and this part has very low density, then it wouldn't be exactly a half. It would be like 3/4 or something. But you would have to calculate it.
Okay, thank you.
Okay.
Just a quick question, sorry.
Mhm.
Does rho only have to be, in this case, symmetrical with respect to z?
If
Yeah. Or over the like XY plane, that is? Like if it's maybe more dense on the like positive side of the x-axis, but less dense on the negative side of the x-axis, that would still be fine because it's symmetric across the z-axis.
Yeah, that's true. Yeah.
Okay, thank you.
Okay. So here I wrote something on double integrals in polar coordinates, but let me just give a quick rundown. I won't go through everything. The things to remember are that when you're converting to polar, don't forget this r becomes r dr d theta. Don't forget the like formulas for Cartesian to polar. Okay, and then cylindrical coordinates. The main things to know here are what are our conversion formulas and what happens if we set certain things constant. If we set, for example, the radius constant, we get a cylinder. I didn't put a nice picture here, but the nice picture is in my recitation notes. I'm actually not too, so someone asked in the chat, will we be given the conversion formulas for the final? I'm actually not too sure about that. Does it say, maybe look at the study guide and see if it says anything? But if not, I'll look into that. Okay, and let's see. Main things again are Fubini's theorem. When we're converting to cylindrical, don't forget you have an r dr theta. Spherical coordinates, main things to remember are these conversions. And what happens when you convert to spherical, you have a rho squared sine phi. Okay. Yeah, any general questions about those conversions?
I have a question. Are we going to review how to find like the bounds for those change of coordinates?
I didn't include any examples, so I did not. Maybe not.
Okay.
Let me. Yeah, some of our. Let me think.
Because I feel like if it's hard to visualize whatever domain you're trying to integrate over, it's hard to sort of find the like the bounds, but I don't know if there's a general like rule or steps you should follow to do that.
Yeah, so with these kinds of like converting to cylindrical or spherical, a lot of it is practice, like trying to recognize what common shapes are going to use what like conversions. So if you ever see a sphere in general, you want to convert to spherical coordinates. So let's say I will make up a quick example. We have this sphere and we want to find the region outside, inside the sphere. Sorry, no, let me just draw a picture. Pretend this is v equals pi over 3. So we want to find the region that is bounded by the cone and the sphere. Meaning I have this highlighted region. Then what would my bounds for spherical coordinates be? Okay, so rho goes from what to what? It starts at 0. And our radius goes out to 1 because we have our entire sphere, including like the curvy part. So it goes to 1. What are my phi bounds? Phi, I can use the cone equation that they give me. They already give me what angle this is. It's pi over 3. And so I should go from 0 to pi over 3. What are my theta bounds? I can imagine collapsing this flat. If I collapse the z-axis, I should still be left with a circle in the xy plane. So there's no restrictions. Theta is still 0 to 2 pi.
How did you get that pi over 3?
They have to give you an equation of a cone. And so say they gave you the equation of the cone in like Cartesian coordinates, meaning regular coordinates, then what you want to do is convert it to spherical coordinates. And in spherical coordinates, any cone is always given by phi equals some number. And so I would get, like, I would solve for pi over 3, or maybe they gave me pi over 3. Okay. A question in the chat: if the base of the cone started at the circumference of the sphere, how would the bounds change? So meaning like you have a sphere and like this.
I meant like the bottom circumference.
Oh, like this?
Sorry, like it would have the same like inverted shape, but it starts at the bottom. I think it's in one of your notes.
Oh, like this?
Yeah, and then the top part, it still ends at the top of the circumference.
Oh, like that.
No, sorry. Like the pointed part is at the bottom, and the upper circle of the
Oh.
cone is touching the top of the
Like
sphere.
that.
Yeah.
Ah, okay. Let me. So I would say. I would say to use cylindrical instead of spherical. I don't remember how I did it in my notes, but for spherical, usually it's better to use spherical if your row can start at 0, like we have here. 0 goes to whatever
Okay.
radius. But here I don't have like a starting row point, like row could go up to 1 here, but at this point, row stops at whatever this like radius is. I don't know what radius that is. So maybe I want to use cylindrical instead. What's tricky about cylindrical now, though, is that what does cylindrical do? I do dz, dr, d theta, which means I need my z bounds. And so if I draw a line in the increasing z direction, in this half of the cone, my starting curve is this line here. But if I drew a line on this side, my starting line is this line instead. And so I would have to break this integral up into 2 parts. I would do the integral of the green part plus the integral of the purple part. So just focusing on the purple part. Actually, you could just, if it's symmetrical, if it turns out that it's symmetrical, you could do the purple part and then multiply by 2.
Okay.
So the purple part, you would have z goes from whatever the blue line is. And so you could like, they have to give you an equation of a cone. So you want to use that and find 2 points and find what that line could be. So find line. And it exits at, so now it depends again on how this was drawn. If your region is only just the cone part, so like it's exactly touching my sphere, but just like that. but I'm not including this like top curvy part of my sphere because, you know, cone is flat, then my Z would go to whatever Z value this is. There, top Z value in black, right here. And then when I collapse it to the XY plane, what happens? I don't get, let's say the sphere has radius 6. I don't exactly get a circle of radius 6. That's not true because this cone doesn't go all the way to 6. So I need to find like, what is this point here? What happens to that point when I collapse it down? So technically I have this cone, I collapse to the XY plane and it only gives me this circle, the green circle. And so again, I would have to like use my equations for the cone and the sphere in order to see what that point is. So like I set both equations equal to each other and solve. Those would be my R bounds. And then theta, I have my entire circle, so 0 to 2 pi. Okay. Yeah.
Sorry. Oh,
Mhm.
quick question. I'm just confused on like the bottom bound for Z. Like, wouldn't the bottom part be a surface?
Yes. So, oh, okay.
The fuck?
So let me think. So I guess it would be a so you would be given like, so you're given an equation of a cone, given an equation of a line, and let's see, if you take the cone equation, what is a cone usually given as? Oh, wait, they should give you the, I think it should be given. What is an equation of cone? Equation. So a cone is sometimes written as x squared. So a cone is usually written as r squared equals squared plus, so z squared equals x squared plus y squared. So then you could get z equals square root of x squared plus y squared plus minus. So that would be
Okay.
bound for z.
Okay, I see. Thank you.
Okay. So let me, okay, so this is, yeah, so a lot of like just practicing, for example, what if a cone was this way? This is, say this is still b equals pi by 3. And I wanted to do spherical coordinates. I would have some rho bounds, some phi bounds, some theta bounds. What are my phi bounds going to be? Well, it's the angle that you make with the positive z-axis. So if my region is exactly this cone here, my phi starts at pi over 3. Where does my phi end? It ends over here. What is that angle? That's like pi over 2 plus pi over 3. So this entire angle here, that's pi over 2, 90 degrees, plus pi over 3, which is 3 pi over 6, plus 2 pi over 6, 5 pi over 6. So those are some like ways that phi could be changed. Okay, let me go to substitutions. Okay, so the thing to know, to memorize about substitutions is that you should memorize this change of variables theorem, or even memorize change of variables. Okay, and what it says is that if you have like variables over here, d variable, whatever, you want to take the absolute value, it equals the absolute value of the Jacobian, the determinant of this Jacobian matrix, and then your other variables here. So let's do an example because, right, we can follow this formula, but what matters is applying it. Oh, and also remember that if you were trying to find a Jacobian matrix where X, Y, and Z are your outputs, U, V, and W are your inputs, then it turns out that if you wanted to use U, V, W as your outputs instead, it would be the inverse. This inverse equals this, where this notation is saying like Jacobian matrix with X, Y, Z as outputs and U, V, W as inputs. Okay, so let's do an example. Okay, so this is from the spring 2017 final, number 9. Okay, so we want to compute this integral, and it looks very hard. Right, but we can use change of variables, and they give us the variables. They say u is x, and v is 2y minus x. So let's see how we could fix this. So actually, let me see if I have I think this one might be harder instead. Let's do this one. Yeah, let's try this one. Okay. So they give you this function here. And we want to convert this triple integral into something with u, v's, and w's. So they've nicely given us what u, v, and w should be. They've said that u is x squared minus y squared. So let's write down what we have. I know u is x squared minus y squared. V should be z x plus y. And w should be 1 plus 2z. They've given that to us. What is our goal? Have x, y, z's here. I want to rewrite it as a u, v, w thing. So what do I know from the change of variables theorem? I know dx, dy, dz equals to the absolute value of whatever variables I wrote here, I should write on the top. So x, y, z. What are the variables I want to change to? Those are u, v, w. du, dv, dw. But we notice a slight problem because this requires, in order to calculate this Jacobian, this requires us knowing like what is x equal to, y equal to, z equals to, so that we can take the partials and get our Jacobian matrix. But we don't have these. We only have that u equals something, v equals something, w equals something. But what do we know? We know that this Jacobian is equivalent to doing, if I wanted to do u, v, w on the top, then I can take the inverse. Right, so let's find this Jacobian, take the determinant, and then do the inverse. Then my results will equal exactly what I wanted. Okay, so I have that. What is, so partial of u, v, w, x, y, z. Remember the outputs correspond to rows, inputs correspond to columns. So I look at my first output, x squared minus y squared. I take the partial with respect to x, that gives me 2x. Partial of this with respect to y is negative 2y. Partial with respect to z, there's no z, so it's 0. Now I look at my second output, and I take the partial with respect to x, that gives me z. Partial with respect to y is z still. Partial with respect to z is x plus y. And then finally, partial with respect to x with respect to y and with respect to z. Okay. Now, what is the absolute value of this determinant? So I'll write determinant. How should I find this determinant? I can use minor expansion, right? And I can use minor expansion on any row or any column I want. So what if I just choose 2 times this determinant, right? In other words, I have 0 times this determinant is 0. Yeah, so minor expansion. For example, let me choose the third row. So I start with 0. I do 0 times, I imagine crossing out that row, crossing out that column, and I want to multiply by the determinant of the remaining matrix. So this remaining matrix is that. But note that it doesn't really matter. I don't have to actually write this out because 0 times anything is 0 still. But I will just write it out so we can see it. And then for minor expansion, the signs alternate. So again, I'm looking at the third column. I've used 0. And I look at the second term, so minus 0 times, imagine canceling out that row, canceling out that column. I have 2x, z, 0, x plus y. And then I add my last number, which is 2 times what's remaining. Cancel these out. What's left is 2x, z, negative 2y, z. This means my determinant is 2 times 2xz minus negative 2yz. In other words, 2 times 2xz plus 2yz. Let me factor out a 2z. So I'm taking out the 2z's. So I have a 4z outside times x plus y. So this is me simplifying it. What is, okay, so I have that. Now, what did I want? I wanted, okay, let me just write this whole entire expression. I wanted this. That's equal to the inverse of the Jacobian that I did find. So in other words, it's equal to 1 over the Jacobian that I did find. du, dv, dw. In other words, it's 1 over absolute value of 4z x plus y. du, dv, dw. So for my change of variables theorem, I have this statement. When I do change of variables, what are the 3 things I always need to change? I always need to change bounds, integrand, and differentials. Sometimes it works out nicely. I can just look at the bounds, change those. I can just look at the integrand, change those to u, v's, and w's, and change the differentials using this formula. And it works out fine. But other times you might want to, you might have a problem kind of fixing your integrand. So let's rewrite let me write my integrand. So, and I'll move this down so I can see it better. X, dy, dz. Okay, this is what I want. Sometimes, and what is my, okay, I keep saying sometimes, let me copy this u, v, w. Okay. Sometimes it works out nicely that this integrand I can immediately write as u, v's, and w's. But I have a problem. I don't see an x minus y in my u's and v's or w's, right? I see like a z x plus y, but this is squared and this is cubed. So I can't really exactly simplify this into u's, v's, and w's. So let me not do that yet. Let me first make sure I plug in my differentials. So I have my integrand. What is dx, dy, dz? That was what I just found. Dx, dy, dz equals this. So it's 1 over 4z x plus y du, dv, dw. Now I can see, does anything cancel out? Well, things do cancel out. A z cancels out here. And an x plus y cancels out here. So I have triple integral of z x plus y squared x minus y all over 4 u, dv, dw. Okay, but it still doesn't look like my u, v's, and w's a little bit, right? But what exactly is x squared minus y squared? I can factor out x squared, or I can rewrite it as x plus y, x minus y. So maybe, oh, sorry. Maybe do I see an x plus y, x minus y somewhere? Oh, I do, right? So let's kind of rewrite our integrand. So I have a fourth z, x plus y, x plus y, x minus y. Because x plus y squared is just x plus y times x plus y. And now I see, what is this? Z plus x, z times x plus y. That's my v. And what is x plus y, x minus y? That's my u. So now I have triple integral of a fourth v u du dv dw. And if they gave you bounds, you would change the bounds to use v's and w's. Okay, and so that is, yeah. Any questions on that? Is it not okay to use? Yeah, it's fine. So the question is it okay to not use W when doing U sub? That it's okay that we don't have a W here. Like you don't need all your variables here. The only thing you have to do is just rewrite this so that you only have, you don't have any X, Y's, or Z's. It's the idea.
So for the bounds, we would just have bounds for x, y, and z, and we just plug in the values that we have in u, v, and w, etc., and we'd find them this way, right?
Yeah, exactly. So if you have, let me think of, so for example, if in the original problem, say you had the first bound for like x equals to, I don't know, I'm making this up. So maybe this doesn't work out nicely like that or something. Okay, no, I'm not gonna make it up because I don't think it's gonna work out. But I do have the next example, which I won't do yet, which the bounds do work out. So you can see a little bit about how it works.
Yeah, thanks.
Okay. Now we have scalar surface integrals. Okay, so surface integrals, what are those? Right, so for any area, for d sigma, you can either write d sigma as, what you're always going to do is, let me have, so this is the formula. First, parameterize your surface. Then you can take the partial with respect to one of your variables, cross product with the partial with respect to the other variable. And then you take the length of that and you write whatever variables you took partials with respect to. So du, dv. Sometimes another formula that is that like people use for surface area elements is also this formula, which also usually works. So that's square root of, you have one of the partials squared plus the other partial squared plus 1. Okay, so we can do an example.
Sorry, Iris, could I check when do we use which formula? Like, how do we know which one to use?
So I would like to say I think it always works. I think it always works. I would recommend, maybe there are some cases where it doesn't, and I don't remember, but this formula usually always, like this formula should always give you the answer. And if you want to like double check your work, you could try this or use this and double check. Yeah. Okay, so let's do an example. Yeah. Okay, so like, for example, okay, we can like check it for this. So what happens, we have a surface which they've parameterized. Okay, the notes, so someone sent me a chat. Oh, okay, yeah, that sounds right. So the cross product version, this version. Oh yeah, okay, this is true. This is very true. Thank you, person who sent me the message. You can only use this formula if you have a parameterized surface. So if you have a surface and you decide to parameterize it, or if they've given you the parameterized version, you want to use the cross product way. This way, you should only use if they give you like an explicit implicit equation for the plane. Implicit. Implicit. Yeah, equation. So yeah, that's why. So in other words, if they give you like, I don't know, surface z is like x squared plus y squared 3 or something, then that's how you can take the partial with respect to x directly from this implicit equation. Take the partial with respect to y directly from this. Whereas if you're given a parameterization of your curve, your surface, like something here, something here, something here, then you want to use this formula. Okay. All right, so let's do an example. So we have a parameterized surface, and it's given to us parametrically. So we want to find what is the surface area element. Surface area element, d sigma. That's going to be the length of my parameterization is called S. So I'm going to take S with respect to U, cross it with S with respect to V. And then what are the variables? Like my input variables, they're U and V. Okay, how am I going to find these partials? Let me find the Jacobian matrix, because we know that in the Jacobian matrix, yes. How do I get the Jacobian matrix? I take the partial with respect to U and I take the partial with respect to S, or yeah, V. Okay. So what is the partial with respect to U here? 0. Partial with respect to V is 2V. Partial with respect to U is this is 2U. With respect to V is negative 2V. And then 2U is 0. Now I can take the cross product. There's lots of, is this Jacobian the same as the DF notation that Grice uses? Yes. Yeah, DF. I just use a different letter. Instead of F, I used S, because that's how they labeled it. Okay, how do I do a cross product? So recall that you can do it multiple ways. I usually like to do, let me do the IJK way. So you write IJK, you write each of the vectors as rows, or if you wanted to do it IJK this way, also works. And I take the determinant. So that means I have what is the I component? I have 0 minus negative 4UV. That's the ith component. Minus, I have 0 minus 4UV. That's the j component. Plus 0 minus 4UV. That's the k component. So I get 4UV, 4UV, negative 4UV. Which means that what is d sigma? If this was my cross product and I want to take the, yes, I did this through minor expansion using the top row. So if you do it the determinant way, you should always do minor expansion through the top row. Okay, so we have d sigma is this cross product, the length of it. Length of any vector is always square root of. You take each of the components, square them. Each component squared. This last thing squared. du dv. Okay, and we can simplify this a bit. 48 squared v squared. In other words, 4 square root 3 uv u dv. And in order to find the surface area, I do recall, I keep saying this, smiley face, d smiley face. So surface area is going to equal 1 d sigma. In other words, 1 times what is d sigma? 4 square root 3 uv du dv. What are my bounds? Well, for that, I look at the beginning of my problem. They gave me nicely the bounds. So I can just take their u is 0 to 2, v is 0 to 3. Okay. Any questions on surface area? Okay, so Let's go to volume 4 then. All right. So volume 4, we have all of these stuff. So we had all those line integrals, the gradient vector fields, Green's theorem, and most recently Stokes divergence, right? Okay. Surface line integrals of scalar functions. Takeaway here is that if you're given a scalar function, like scalar function meaning they give you f is like xy plus y squared, something like that, lowercase f, then the formula you always use is the length version. So you take the derivative and take the length. That's this formula. Always 2 steps. First, plug in your parameterization. Second, what is like your differential? It's going to be the length version of your derivative, dt. So that's for scalars. Okay, we can do. Okay, does anyone want to see put a thumbs up if you want to see an example? Or we will move to, okay. So consider this scalar field, for example, and we're trying to compute the integral of it. So the first thing I know is that I'm given a scalar field, which means I want to use the length version of my formula. Here dt. Wait, what is my, how did I write it? Yeah, dt, okay. The length version. And you'll recall that there's another version where you're like just plain dot producting by the vector. That will be in the next slide. So we don't want to confuse these two. For the scalar field, we always use the length version. So what am I going to need to do? I always, no matter what, need to parameterize my curve. What is my curve? It's a quarter circle from 2, 0 to 0, 2. So let's draw this. I have 2, 0 to 0, 2. So my curve goes this way, in this direction. So to parameterize this, what is the normal parameterization we use for a circle? For a circle, we usually say it's cosine sine. But since that's for a unit circle, since our circle has a radius of 2, our parameterization, we're going to want to multiply by 2. Right? And you can also, yeah, so we want to multiply by 2. And you can check, where should theta start from? Well, whatever I plug in for theta first, I should get my point 2, 0. So what is theta here usually? It's usually 0, right? And let's see, if I plug in 0 here, what do I get? I get 2 times 1, which is 2. And I get 2 times 0, which is 0. That's good. My starting theta gives me my starting point. Where does theta go till? Well, what angle is this? Pi over 2. And let me check. If I plug in pi over 2 here, what do I get? I get 2 times 0, which is 0. That's right. And 2 times 1, which is 2. That's correct. My ending theta gives me my ending point. Now I take the derivative because I'm going to need it, right? According to my formula. The derivative is -2 sine theta to cosine theta. What is the length of this derivative? That's square root of each of the components squared. So I have -2 sine theta squared plus 2 cosine theta squared dt. Actually, let me not write the dt for now. Actually, I'll write dl equals this dt. Right, this is the formula I'm following. dl equals that dt. Okay, so I have dl equals square root of that dt, which is square root of 4 sine squared theta plus 4 cosine squared theta dt, which is square root of 4, because sine squared plus cosine squared is 1 dt. So I get 2 dt. Now, what am I doing? I'm trying to find according to my question, I'm trying to find the integral of f dl at the boundary, at my parameterization, gamma. Gamma f dl. What does that equal? Well, it equals, in general, let me write the general formula. We have FDL equals integral AB. We take our function, evaluate it at our parameterization, and multiply it by the length of dr dt. I guess I called this gamma here. It's gamma. Okay, so I have my function. What is my function? It's 1 plus x squared plus y squared. Okay, that's a side note. So if I plug in my parameterization into 1 plus x squared plus y squared, what do I get? I get 1 plus x is 2 cosine theta squared. Y is 2 sine theta squared. What is my length dt? Well, I just found it's 2 dt. Okay, and we want to be careful about parentheses. This is all multiplied by 2 dt. Okay. Oh, I guess in this case, what was I? Sorry, these, all the t's are thetas technically. Theta, because I took the derivative with respect to theta. Sorry about that. Change these to thetas, theta. Okay, what is my theta going from? Well, I found it when I parameterized my curve. It goes from 0 to 2 pi. Theta goes from 0 to 2 pi of, what is this? This is 1 plus, it's going to be
pi over 2.
Yes, wait, pi over 2. Oh yeah, sorry, pi over 2. Here it's pi over 2. So I have 1 plus 4 plus 4. No, just 1 plus 4 regularly times 2 d theta. So I get theta equals 0 to pi over 2 of 5 times 2 is 10 d theta. So I get 10 theta from 0 to pi over 2. In other words, 5 pi. Okay, how did I do this? Let me write it all out. I have this squared theta, 1 plus 4 times cosine squared theta plus sine squared theta. This is 1, so I just get left with 1 plus 4. Okay, that was for a scalar. Why is it pi over 2? It's pi over 2 because when I parameterized my curve, my theta went from 0 to pi over 2. So I should follow the bounds that my parameterization gave. Okay, any questions on that? Okay, then we have line integrals of vector fields. Okay, so let's recall that we can always sketch a vector field, first of all. How do we sketch a vector field? I can take whatever vector field they give me and plug in points, and I draw those arrows. So for example, if this vector field was just x comma y, where c is 1, then I take a random point like 1, 1. I plug it in here, it tells me my vector should go 1 up, 1 to the right, right? 1 right, 1 up, and that gives me this vector. And I can draw it for every single point, and I get this kind of picture. This vector field also gives this picture. How do I take the integral over a vector field? This is the formula where you're not multiplying by the length anymore. You're dot producting it with the derivative, right? So if you ever see, like, they give you a function with capital F, or they give you the function as written like something I plus something J plus something K, then you want to use this version of the formula, not the one we just did. Okay, but the idea is the same. You still want to first write your parameterization, plug in your parameterization into your function, and then you dot it by this differential, which we just defined, or which we will define. So, okay, actually, I don't have an example for this type. But yeah, so like the idea is that you will have some Like you'll find your parameterization gamma equals, say, something, something, something. I'll call it ABC. You take gamma prime. Let's say it gives you DEF. My integral of f dot dr is going to equal where my parameterization t goes from, I don't know, 1 to 2. 1 to 2 of, I take my function and I plug in my parameterization, and then I dot it by the derivative, dt. So my function, they should give me as, right, this is some I, this is some j, some k. So it should be some vector with 3 components. My derivative is def dt. And so I get integral of some number dt. So that's how this type works in general. Okay, and so here I have just a summary of like when you should do what, like you're finding a line integral. If they give you this lowercase f, that means that's a clue that they want you to use the scalar version, meaning this version where you're doing the length of the derivative. If they give you like these differential elements, like an I, like your function is written as like 2i plus 3j plus 5x squared k or something. Or say they say your function is 2dx plus 5y dy. Those types of like wording, that means that they want you to use the vector version where you're doing the dot product. Okay. Oh yeah, I wrote these like here basically. Okay. Any questions on these line integrals so far? Okay, and then what happens with these line integrals? We have some applications. So we have work done. So work is going to be the work done along some curve, gamma, is going to be given as exactly f dot dx. So that's the vector version, this version. We also have flow. Flow along some c is f dot dr as well. And specifically for this like case, from flow, we get something called circulation. Circulation is just a special case of work, specifically where your path is a closed loop. And what a closed loop means is that it starts and it could do whatever it wants, but it ends at the same point. That's a loop. So you have like work done along some vector field, and circulation is just a special case of work where you have a closed loop. Okay, and with that, we can define what is circulation. Circulation is mdx plus ndy. This is going to tell you like when you're doing, so my notation I use is f dot dr. When you're doing f dot dr, what you do is you plug in your parameterization, your x component of the parameterization for m, the y component of your parameterization for n, and the d variables are telling you like what the derivatives you're multiplying by are going to be. So like in other words, the dx and dy come from the derivative of gamma. Okay, and what circulation does is it measures the tendency of your vector field to flow on the curve, like how much does it tend to flow in the same direction of your curve. And flux is going to be the net tendency of your vector field to cross the curve. And so notice that we have for flux, it's mdy minus ndx. Okay. Next we have okay, any questions on those? Okay, so we have gradient fields and the fundamental theorem of line integrals. Okay, this is a very popular question. So remember what the fundamental theorem, or also called independence of path theorem, IOP. Remember what that does. Okay, so a field is conservative, in other words, path independent. What does that mean? It means that regardless of the path you integrate over, you should still get the same answer. And it's conservative if you have a gradient. So you can check whether or not your field is a gradient. If it is, then your field is conservative. They mean the same thing. If your field is conservative or it's a gradient field, then I can use the independence of path theorem. What does that say? That says that instead of actually doing all the hard work and taking that integral, which would take a lot of time, you can instead find the potential function. This lowercase f is called the potential function. And you plug in your endpoint into f, and then you subtract, you plug in your starting point into f. So hopefully, yes, I do have an example coming up, but let's keep going a little bit. So how do you check if you can use independence of path theorem? We have the component test. But the component test is you're trying to like check every single partial that you have. So like if you have some function, like 3i plus 5x squared y plus, j plus 5z squared k, like that. I call this m, and I call this n, and I call this p. Component test says I need to check that partial of m with respect to y. So first component with respect to second variable should equal second component with respect to first variable. So you see how they're kind of like flipped. And then I need m with respect to z should equal the third thing with respect to the first thing. And then n with respect to z should equal p with respect to y. Another way to remember this is how do you remember what to check? These kind of look like the things from the curl, right? Because this is m over y minus n over x. And that's exactly the kth component of your curl. So if you ever forget like what exactly you need to check, just imagine how do you find the curl? You do like the ijk thing, partials, m and p, right? For the curl. And for example, this is the ith component minus whatever j component, whatever k component, and see how this is exactly this. In other words, to get a gradient conservative field, we set like the curl equal to 0, 0, 0. So this equals 0 means partial n over z equals p with respect to y. Okay, and here I just wrote a little bit about like different wording. These are all equivalent. If you say f is conservative, that's the same as saying it's a gradient vector field, which is the same as saying it's a gradient one form. And with all of these, you can always, that means it passes the component test. Okay, so that's just in case you hear me saying different wording or you hear other problems with different wording. Okay, but let's do an example. So here we have spring 2017 final number 7. It asks us to compute the work done by this gradient field. And let's see, they say capital F is the gradient of this function here. They're already giving us a very nice clue. Okay, and we're trying to find this integral along the helical path. Now, this capital F, so in general, we're trying to find integral f dot dx. If capital F is a gradient field, then we can use independence of path theorem and use IOP. Is capital F a gradient field? It is, because they wrote it as the gradient of some function. So another way they could have written capital F is, say they didn't say this. Say they gave you F is 1, 2, 2z. They gave you F is this. You would check that using the component test that it is a gradient field, and then use independence of path. But they already gave us, the reason they gave us capital F in this form is so that we don't have to find that potential function. They already gave us the potential function. The potential function is x plus 2y plus z squared. Because capital F is the gradient of this potential function. And so, like, if they had started off with this, we could work backwards and find potential, like integrate. and find the potential is exactly what we have. Okay, so independence of path theorem says f dot dx along some curve is f of b minus f of a. What is the ending point, b? Well, for that, we need to see what is our path. Our path is given as cosine t, sine t, and t, where t goes from 0 to 2 pi. So what is t equals 0? At t equals 0, our point is, I plug in 0, so I get 1, 0, 0. And at t equals 2 pi, what do I get? I plug it into here, and I get 1, 0, 0 again. And so that means that when I do the independence of path theorem, I have f at my endpoint, which is the 1, 0, 0, minus, sorry, this should be 2 pi. That's my ending point. Minus f at my starting point, which is 1, 0, 0. So I plug this into my potential function, which is x plus 2y plus z squared. And what do I get? I get 1 plus 0 plus 2 pi squared minus 1 plus 0 plus 0. In other words, I get 4 pi squared.
Isn't the result a vector as well, or is it? Or is the scalar when we subtract two fields?
So it should be a scalar because our function, our potential function is always a scalar function. So you get like a number here. If you plug in a number and you get out a number.
Okay, thank you.
Okay, any other questions so far? Okay, next we have a quick refresher of del operator. Oh, so the key takeaways are that, okay, this is very important, I think, just to visualize if you're doing things correctly. If you start off with a scalar function, what does gradient do? Gradient gives you out a vector field. Curl takes that vector field and gives you a vector field again. Divergence takes that vector field, gives you out a scalar function. And you have three main things that we learned with this triangle thing. You have the gradient, which, right, you should still get a vector, these three things. Curl, you also get a vector, that's this thing, which kind of looks like the component, or which is the component test, essentially. And divergence, which gives you a scalar because you're adding things. Okay. And so those are in 3D. If you're in 3 dimensions, meaning you have X, Y's, and Z's, you have each of these things, like you should have numbers there. If you're in 2D, what changes is that the gradient, well, if you're in 2D, you don't have a Z component, right? So the Z component, you have a 0. Sometimes you just don't write it. You just say the gradient is this. What's important to note for the curl, if you're in 2D, is that you can try to calculate it, like the actual curl, and you'll see that you get 0 for the first 2 components. So when you're in 2D, you only get kth component of curl. Component of curl. Why is this important? This kind of looks familiar, right? It almost looks like Green's theorem. It is like Green's theorem, basically. Green's theorem, we have like double integral of n over x minus m over y. Why did that happen? It's because in Green's theorem, we're always dealing with 2D surfaces, 2D things. And so we see that if we're in 2 dimensions, our curl only gives us the kth component. So that's why in Green's theorem, you only have a double integral of just this single thing, the kth component of the curl. Whereas if you're doing Stokes' theorem, that's in 3D still. Stokes was like, we did the curl, exactly. And you would have 3 things, 1, 2, 3. Because you're in 3 dimensions, so you should have 3 things. But in 2 dimensions, you only have the kth component of the curl. That's why Green's theorem had that. And then for divergence, it's also these partials, but there's no z component, so you add 0. Okay, and remember that if you do curl of gradient, you get 0, and divergence of curl is also 0. Okay, and yeah, here's some interpretations. I think I sent some more conceptual understandings in email the week we did this. You can look back at that. Okay, Green's theorem. When can we use Green's theorem? We can only use it if our problem is in 2D, first of all. Also, we should have a simple closed plane curve, meaning your curve doesn't cross itself. You shouldn't have like a weird infinity thing. You should have a closed curve, meaning starts and ends at the same point. And plane curve means that it should be flat. We're in 2D. Green's theorem, you have two versions, circulation version and flux version. Note that you can derive the flux version from the circulation version. So if you don't want to memorize two things, you can just memorize what is flux and memorize this Green's theorem for circulation. Okay, and that's exactly what I just said. Note that when you're trying to find flux though, don't change like how you choose M and N. M and N always come directly from your function that they give you. So say F is like 3i plus 2j. No matter what, any formula you use, M and N is always going to be 3 and 2. You don't change your choice of M and N based on this formula. Okay. And so here, yeah. When can we use Green's theorem? Simply connected domain, meaning there's no holes anywhere. Holes are bad. Okay, here we have an example. Wait, here. Okay, so if we're trying to consider this path integral and integrate it over a circle of radius r centered at the origin, compute the integral over this circle. So, and they say think first. So let's think. Do we want to actually parameterize our circle, plug in the parameterization, multiply by the derivatives? We could, but that seems like a lot of work. And also they said think first. What about, can we use Green's theorem? Question mark. Well, we can use Green's theorem if our curve is closed. And we do have a closed curve. They say it has a circle of radius r. So circle of radius r. It is closed. So let's use Green's theorem to calculate this integral. Green's theorem says what x squared y plus 1/3 y cubed dx plus x dy over my curve equals, this is m, this is n. Green's theorem says I do n over x minus m over y. Okay, maybe let me actually write this as if you were doing the exam. You would want to see like, you should write something like this, like write the formula for Green's theorem first. Nx minus my dx dy. Okay, and then we can say this equals double integral of what is n? That's x. Partial with respect to x is 1. Minus m with respect to y. That gives me x squared plus y squared. Be careful of parentheses. Dx dy. Now, again, I could do this in Cartesian coordinates, but that would require, like, what are my bounds going to be? I'm going to have like y equals square root of like 1 minus x squared or something. Like I'm going to have square roots in my bounds because that's how I write a circle. So instead, let me convert to cylindrical or polar, I guess, because we're in 2D. Let me say polar. Okay, what happens when I convert to polar coordinates? I have an entire circle of radius r. So r starts at 0, and it goes to the radius. The radius they gave me is capital R. Theta, we have our entire circle. So theta goes from 0 to 2 pi. And then we have to change our integrand. We have 1 minus, what is x squared plus y squared in polar coordinates? That's r squared. Okay, and then finally the differentials, when I convert to polar, it becomes r dr d theta. So I can do this all out and I'll get this as my final answer. Okay. Now a follow-up is part B. Using your answer to part A, which we just found, what value of r maximizes the integral? And it says, show me that you remember basic single variable calculus. Okay. So we're maximizing an integral. How do we maximize things in single variable calculus, according to the hint? We always start with a function, and then what is maximizing mean? It's like finding the local extrema, a maximum or a minimum. So if you have a function, what did we do in single variable calculus? You take the derivative, set it equal to 0 to find your critical points. And then based on your critical points, you can use the first derivative test or the second derivative test to see if it's a min or max. Right? And so that's what we're going to do. Imagine this is our function. How do I find the critical points? I take the derivative of it with respect to r. So let me copy my expression. And I set it equal to 0. What is the derivative of that? I need to use product rule, or actually I don't need to use product rule because 2 pi is a constant. I can take the derivative of this thing. What is the derivative? I bring the 2 down, so it cancels out, so I'm left with r minus the 4's also cancel out, so r cubed equals 0, which means r minus r cubed equals 0. Now I can factor out an r, so I have 1 minus r squared equals 0. This means I have r equals 0 and r equals 1 as my critical points, plus minus 1 actually. Now I have my critical points. How do I know if it's a max or a min? Well, what could I do? I could plug these values in to my original function and see which one gives me the largest number, because I'm trying to maximize. So I can plug in r equal to 0 into my highlighted equation. What happens? I get 0 squared over 2 minus 0 times 2 pi, that's still 0. What happens when I plug in positive 1? I get 1 squared over 2 minus 1 squared over 4 times 2 pi. Okay, what happens if I plug in negative 1? But we don't have to plug in negative 1 because they say what value of r greater than 0. So I can just look at 0 and 1 and I see plugging in 1 does give me a bigger value than 0. So r equals 1 gives me the max, maximizes my integral. So question in the chat says, do we need to make the Hessian? Do we not need to make the Hessian and check if it's a minimum? So the Hessian is where we are in a question of multivariate. So we use the Hessian if your function is a multivariable calc function, meaning you have like f of x, y, z equals something, something, something. But right now we're in a question of single variable calculus. Our function only has one variable, it's just r. So we don't need to do a Hessian or anything. It's just one single variable calculus function. So we use single variable calculus techniques, which is the critical points and then first derivative test, second derivative test. And that's what I kind of like. If you wanted to do the first derivative test with like you make a sign chart thing, like you could, but it also works if you plug in your value and see which one gives you the largest number. Yeah, you could do the second derivative test if you wanted to, like you would take the derivative of this again and then plug your values in. So that was like first derivative test and second derivative test from like single variable calc. Any questions on that? Okay, so that was a nice problem. Then we have differential forms. So these are the forms language stuff. Okay, so we have a zero form field. That means they just give you a regular scalar function, lowercase f. A one form field is you write, so say they give you a vector field like f1. So vector field is always written with like the I notation, like IJK stuff. K. And how you translate it to forms language is you keep those same coefficients, but now we have dx, dy, dz instead. And then we have the flex two form field. That's the same thing, but you have these wedges instead. And then a three form field, you have three wedges. Okay, and the order for this flex two form field matters. Whatever is in front of the dy wedge dz term, that's always the first component of your vector field. And whatever's in front of dz dx, that's the second component, etc. So those are general statements. What is the point of these forms? These forms can eat in something and it spits out something. So if I have a one form field, it could eat in a scalar, eat in a vector and it spits out a scalar. If I have a two form field, I can eat two vectors and it still returns a scalar. A three form field would eat three vectors and it still spits out a scalar. So these forms are always eating in some number of vectors and returning out a scalar. And how you do, for example, a two form eating two vectors is you would take the determinant of, you write your function as the first column with your point plugged in, and then you write the other two vectors vertically. For a three form field, you would have that same function evaluated at your point, but now because you have three vectors, you multiply by the determinant of those three vectors. Okay, so we can do an example. So spring 2017, number 11B. So we want to evaluate, and also note that this is one way to do it. You could also not, so this requires converting to like vector language and then doing the determinant. You could also keep it in the forms language if you want, where you know that dx wedge, like wedge products, represent projected area to the xy plane or whatever variable plane. And you take your vectors and you write whatever vectors are in those positions. So, for example, we can do it here. We have a two form and we want it to eat in two vectors. It says evaluate this two form on the ordered pair. Let me do it the forms way. So I can do method one using forms. I can just keep my 2dx wedge dy minus 3dz wedge dx. What does this equal? Equals 2 times a wedge product represents area projected to the xy plane. How do I find area? Like spanned by two vectors. I do the determinant. So I take my vectors. What are the x and y components of my vectors? Those are 1, 0, 4, -2. Then I subtract 3 times. What are the z components? Those are 2 and 3. What are my x components? Those are 1 and 4. And so I get 2 times -2 minus 0 times -3 times 8 minus 3. That's -4 minus 15 or -19. Okay. And I could also do it this way here if I wanted to. If I wanted to do it that way, I just need to make sure I'm writing this in the correct order. So my corresponding function should be 0, -3 because the z wedge dx, and 2. Okay. Any questions on that? Okay, so wedge products, what are they doing? So I mentioned that wedge products give you signed area a triple wedge product gives you signed volume. Okay. So someone asked in the chat, with which theorem do we use the flux one form? So like if you have a one form field eating in a vector, you would take that field and you dot it with the vector. Not sure if there's a flux one form. Oh, I guess, yeah, that would, so if you just have a one form, for example, I think it would be better to convert it to this vector way, where you have this vector, plug in your point and you dot it with the vector that you have. This like method generally works for double wedge and triple wedge. Okay. And so it's like flux over a boundary. So not necessarily. So like this wedge, this two form eating in a vector is not really computing flux. I believe to compute flux, that would be like if you're integrating a two form or integrating a one form. This is more like giving you, so like for example, 2 dx wedge dy itself, that's telling you area projected to the xy plane times 2. Yeah. Okay. So what about if we differentiate forms? Well, if you take the derivative of a 0 form field, that's associated with the gradient. So the point of this page is that if you have a 0 form field, let me take the 1 form field. If you have a 1 form field, you can differentiate it term by term, and you can do that, or you can just take the curl, and it should give you the same answer. That's what this page is saying. And the derivative of 2 form field is associated with the divergence. So instead of actually taking the derivative term by term, you can instead find what is the vector field that corresponds to it, and then take the divergence of it, and then add this triple wedge product. Okay, and so with this summary thing, we have this diagram, right? This was the vector language, and the forms language is the same. So like, and if you do any two combinations, you'll get 0. So like if you take the derivative 2 times exactly, you get 0. Okay, and here was the dictionary, which I'll let you guys look at. So here I have surface integrals of vector fields. The point of this is that, say you're given some surface and it asks you to find the surface area, I would use this formula here. So you can keep it in like forms language. This is some beta, plug in your parameterization, multiply it by this Jacobian matrix. The point of that is that we can use the surface integral when we're doing Stokes and Gauss. So quick thing about Stokes. What is the formula for Stokes? It says that the integral of alpha over some boundary equals if you do the integral of the derivative of it over the actual surface. And this is the general like formula. If you do it in 2D, Green's theorem is just a 2D version of Stokes' theorem. Okay, so I didn't put any examples here, but I'm sure there's lots of examples in the practice problems and practice quizzes. We also have divergence theorem, which is using the form language. If we wanted to do the integral of this 2 form over a boundary, we can instead do the integral of the derivative of it over the entire domain. Note that you can only use divergence theorem if you have an actual 3D closed shape. So if you have like a sphere, use divergence theorem. But if you have like a flat or even a tilted like plane, you want to use divergence theorem. It has to be some like 3D object. Okay. And okay, so I have an example of divergence here. So this is spring 2017 final number 5. Okay. Oh, also if it says like compute the flux, that's a signal that you usually want to use divergence theorem, or I should be saying Gauss's theorem, sorry. Divergence, Gauss, same. If it asks you to do flux of curl, you should use Stokes, generally. Okay, so this question is saying find the flux of this vector field through the boundary of the unit ball. Okay, and they say if you're panicking about the derivative of secant tangent, you shouldn't be panicking about that. The reason is because maybe you tried to use Stokes' theorem. Stokes' theorem would require you to do like the derivatives, right, when you're finding the curl. And so that would be a lot of work. So they're saying, oh, don't use Stokes' theorem. That's not the correct way. You should be using Gauss's theorem. So Gauss's theorem, what does it say? It says that F dot df. So whenever you use a formula, say like Stokes or something, like say the name, and write the formula. And then you can start plugging in points. So what is the derivative of, so let me call these M and P, M with respect to X, N with respect to Y, P with respect to Z, dV. What's the derivative with respect to X of the first thing? Well, I get 2, and there's no X's here. Partial of this with respect to Y, there's no Y's, so I get 0. And partial of the last thing with respect to Z, there's no Z, so I also get 0. So I get the 2 times the triple integral of dV. What is triple integral of dV? That's volume of my unit ball, my shape. I have a unit ball. What is the volume of any sphere? Volume of any sphere is 4/3 pi r cubed. And it's a unit ball, so radius is 1, which means I have 4/3 pi r 4/3 Apple pencil 4/3 pi. I get 2 times 4/3. Okay, 4/3 pi. And
Just
so
a quick question.
Yep.
So you used Gauss's theorem for this, right?
yes,
Because it asks for the flux.
yes. So if it says like find the flux of something, that's a clue that you usually want to use Gauss. If it says flux of curl, that's usually a clue you want to use Stokes.
Okay.
Yep. Okay, and so you see how much like using Gauss, that problem was so much quicker, as opposed to if you maybe tried to do a parametrization or something, or Stokes' theorem would have been incorrect as well. So Gauss's theorem makes it nice and quick. Okay, any questions on that? Okay, and so finally, I have this little summary. Yeah, which is okay, I won't talk about the summary. What are the 3 main theorems we have? Don't forget fundamental theorem. I should have been calling these independence of path theorem, Stokes theorem, divergence theorem. Guaranteed one of these are going to show, at least one of these are definitely going to show up based on past finals. But yeah, that's the end. Any questions? Okay, that's the end of review session number 2.
I